Now that we have known the basics of summation operators, we can now derive the OLS estimators, and that is beta naught and beta 1 from the simple regression model. Okay, so note that we can also write this simple regression model, this equation, as u equals to y minus beta naught minus beta 1 x. Okay, so before we derive the OLS estimators, we need to know two assumptions, and those are expected value of u equals to 0 and covariance between x and u is 0, and we can also write that as expected value of x and u equals to 0. So we know that covariance, so let's assume that covariance of x and u is equals to 0. So we can also write that as, if we apply the formula of covariance, we can write it as expected value of xu minus expected value of x multiplied by expected value of u equals to 0. And so expected value of xu, so we already know that expected value of u equals to 0. So if this one is 0, then this whole thing would just be 0. So essentially, if it's minus 0 equals to 0, so we are only left with expected value of xu equals to 0. So this and this. Okay, so with all that in mind, let's derive beta naught and beta 1. And okay, so our first assumption says that expected value of u equals to 0. Okay, so we can also write it as expected value of y minus beta naught minus beta 1 x equals to 0. Since this is the expected value, if we convert this into summation operator, we can write this as 1 divided by n summation of I equals to 1 to n, and we can write it as yi minus beta naught hat minus beta 1 hat xi equals to 0. So now the hat is because we are deriving the estimates of the population parameters of beta naught and beta 1. So the estimates are beta naught hat and beta 1 hat. So we are just deriving the estimates for the observation of yi and xi. Okay, so now we can also write this as y, since this is 1 by n, we can write this as y bar and minus beta naught hat minus beta 1 hat x bar. And from this we can get the beta naught, we can get the value of beta naught, and that is beta naught hat equals to y bar minus beta 1 hat x bar. Okay, so this is the value of beta naught hat, and now we can derive the value of beta 2 hat. So let's see here. So this is the value of beta naught hat. So our second assumption says that expected value of xu is equals to 0. So we can write this as expected value of x y minus beta naught minus beta 1 x equals to 0. So if we convert this to summation operators, we can write it as 1 divided by n summation of I equals to 1 to n xi yi minus beta naught hat minus beta 1 hat xi equals to 0. So just like in the previous example, we are deriving the estimates. So that's why I've put a hat on beta naught and beta 1. So if we multiply both sides with n, we are getting rid of this 1 divided by n, so we can write it as I equals to summation of I equals to 1 to n and xi yi minus beta naught hat minus beta 1 hat xi equals to 0. So I've just multiplied both sides with n. So now I can write it as summation of I equals to 1 to n xi yi. So I've got beta naught hat equals to y bar minus beta 1 x bar. So I'm just going to plug in the value of beta naught here. So if I plug in the value of beta naught, I'll get y bar plus beta 1 hat x bar minus beta 1 hat xi and equals to 0. So let's write it from here, okay? So if I factor out xi, or if I rearrange it, we can write it as summation of I equals to 1 to n xi yi minus y bar, or we can write, if I factor out minus beta 1, we can write it as minus beta 1 hat summation of I equals to 1 to n xi and xi minus x bar, okay, equals to 0. So from the basics of summation operators, we know that this too has some distinct value. So before we do that, let's rearrange this equation again. So we can write this as summation of I equals to 1 to n xi yi minus y bar equals to beta 1 hat summation of xi x multiplied by xi minus x bar, okay? So from the basics of summation operators, we know that xi multiplied by yi minus y bar is equals to xi minus x bar multiplied by yi minus y bar. So let's just plug in that value. So summation of I equals to 1 to n. So we can write it as xi minus x bar yi minus y bar equals to beta 1 hat, and we can also write it as xi minus x bar whole square. So summation of I equals to 1 to n xi minus x bar whole square. So from this we can now get the value of beta 1. We can write beta 1 as, so we can write beta 1 is beta 1 hat is equals to summation of I equals to 1 to n xi minus x bar yi minus y bar divided by xi minus x bar whole square, and there will be a summation operator at the beginning. So this is the value of beta 1 hat, and this is the value of beta naught hat, and thus we have derived the OLS estimators.
Now that we have derived the OLS estimators, as we have discussed before, the estimates beta naught hat and beta 1 hat are the ordinary least square estimates of beta naught and beta 1. So if we define a fitted value or predicted value for any beta naught hat and beta 1 hat for y when x equals to xi, we will get yi hat equals to beta naught hat plus beta 1 hat xi. So this is the fitted value or the predicted value, as in this is the value we predict for y when when x equals to xi, as in the ith observation. And the residual or the error term for observation I is the difference between the actual value of yi and its fitted value. So if we take the error term ui hat here, it would be the difference between yi and y hat, so yi minus y hat. And we can also write it as yi minus beta naught hat minus beta 1 hat xi. The whole purpose of the ordinary least squares is to minimize the error term or minimize the sum of squared residual through the fitted value. So if we minimize the error, we will get the best fitted value or the most efficient fitted value with as minimal error as possible. So we are basically looking to minimize this value right here. So that is summation of ui hat whole square, and so we are trying to minimize yi minus beta naught hat minus beta 1 xi whole square. So if we minimize this value, we will get the best fitted value there is. And the name ordinary least squares comes from the fact that these estimates minimize the sum of squared residuals. So if we look at this graph, we can see that there are various data points here as in the blue dots. These are the actual value of yi. And if we fit a line through that, we will get the predicted value or the fitted value for these data points. And this is y hat, and y hat equals to beta naught hat plus beta 1 hat x. Okay, so the residual would be the difference between the actual value of y minus the value that lies within the fitted value. So this is the difference here is the residual or the error term.